Okay, welcome back everyone. So last time we stated the cone theorem and the contraction theorem in higher dimensions and stated it more precisely than we did during surfaces. So I want to start by discussing the structure of extremal contractions. So recall if we have an extremal ray in the cone of curves, then and let's assume that it's kx negative. So it lies in this piece of Néron-Severi. Then we stated the contraction theorem, which says that there exists, at least under some conditions, there exists a contraction morphism F, which we'll call the contraction of R from X to Y, that's characterized by the properties that F lower star OX equals OY, and a curve C is contracted by F to a point, if and only if the numerical class of this C is in our ray. Okay, so we want to classify the possibilities for the geometry of these extremal contractions. So let's write it as a kind of definition proposition. An extremal contraction F can have one of the following shapes. And we haven't talked about singularities yet, but in the definition of an extremal contraction, it doesn't really matter if X is smooth or not. All that matters to make sense of the definition, at the very least, is that Kx is Q Cartier, so that intersection numbers with curves and the canonical makes sense. Because in particular, to define a Kx negative extremal array, we needed to be able to intersect with the canonical. So everything I'm about to say, we just need to assume that Kx is Q Cartier, and then we'll figure out the right class of singularities to actually prove that these things exist. So it could be a fiber space, meaning that the dimension drops. Or it could be a divisorial contraction. Meaning that F is birational and the exceptional locus is an irreducible divisor. Or it could be a small contraction which means that F is birational, but the exceptional contains no divisors. Okay, so this proposition gives us a structure of extremal contractions, and really the only part here that's a proposition and not just a definition is the part that if the exceptional contains any divisor, then it actually is just a single irreducible divisor. So the rest of it is just saying, well, either it's birational or it's not, and either it contains a divisor or it doesn't. So the only statement we need to prove is that if there exists some divisor E in the exceptional, then E is the whole exceptional. Okay, Great. So let's take our irreducible divisor contained in the exceptional. So the first thing we know, and this is some higher dimensional version of the Hodge index theorem, is that E dot R has to be strictly less than 0, where R is our ray. Um, and I mean, the reason for this is because E, being exceptional, being in the exceptional locus, has to be covered by curves that are in the numerical ray R, because of the definition of an extremal contraction. You're contracted if and only if you're in the ray R. So whatever classes in R have to live inside of E, but E is exceptional, and so E dot anything inside of it has to be smaller than 0. This is like in the surface case, if we have an exceptional curve, E squared has to be strictly smaller than 0. So, and I think one way you can even, so this higher dimensional analog of Hodge index, and I think you can prove it by actually slicing down by hyperplanes to get down to the surface case. Okay, but on the other hand, take any curve C in the exceptional locus. Then the class of C is contained in R. So then we know that E dot C is less than 0 by this first observation, but that means that C has to be contained in E. Because if it wasn't contained in E, then you'd have an intersection that was 0-dimensional, so you'd have greater than or equal to 0 intersection number. So that tells us that E has to be the full exceptional. So essentially the point was just that this array is one-dimensional, so every curve that's contracted is just a scalar multiple of a single curve, which lies on E. So that's some, and this is why we want to understand extremal contractions for rays rather than for higher dimensional faces, where the exceptional geometry could be more complicated and have many components depending on the different rays in our face. So right, so now let's say a few more words about the actual cases. So in this first case where we have a fiber space, so we have this map X to Y with connected fibers. And let's say that F is a general fiber. And let's also assume for basically everything for the rest of this class that at the very least X is normal. So we have this general fiber. Yeah, so since X is normal, we can take a general fiber that's smooth. Or at the very least normal. Okay, yeah. So the point is that minus kx restricted to F is ample by Kleiman's criterion, which we'll finally prove later today. Because kx, because we're contracting these kx negative curves. So kx dot any curve in the fiber is negative, so minus kx is strictly positive. And so, but actually we know more. We know that this is actually, right, this way, we know that kf is actually the same as the restriction of kx to f. And to justify that, let me draw a picture. So here's y. We have our general point P, and we have kind of x sitting over y. We have our point here, and then our fiber will be something there. So our point we can cut out as the intersection of some Cartier divisors because it's a generic point, so it's going to be smooth. So let's say in this case, our point is like the intersection of H1 and H2. And we're in the surface case. We're in the case Y as a surface just to make it easier, but you can just do the same thing by induction. So then we know that if we let F upper star HI be DI, just whatever the preimages are, then we know that our fiber F, our general fiber, is the intersection of these DI. But also because it's fiber, we also know that DI dot F are all 0. Or DI restricted to F are the 0 divisors. So we take DI and we restrict, let's say DI is some Cartier divisor because we picked a generic point. So a generic point we can cut out by Cartier divisors on Y, at least locally. So our pullbacks are some Cartier divisors on X, and we can restrict them to F, and we know that they have to be the 0 divisor because F is a fiber. And they're pulled back. And so now we can write down a junction. So Kx, let me write it this way, plus D1 plus D2 restricted to D1. This is like KD. Oh no. By a junction on D1, like Kx plus D1 dot D1 is the canonical of D1, and then whatever we have left over is just D2 restricted to D1. And now we can restrict this further to D2. Well, then this becomes again by applying a junction. Now we're restricting the divisor D2 restricted to D1 to D2 restricted to D1, so we get a junction for that. So we get D1 intersect D2, which is just KF. So on the one hand, if we restrict Kx plus D1 plus D2 to F, we get Kf, basically. So another way of saying this is that this is Kx plus D1 plus D2 restricted to the fiber F. But on the other hand, D1 and D2 restricted to F are trivial, so this is the same as KF. Sorry, this is the same as Kx restricted to F, because the D1 and the D2 don't contribute at all in this restriction. Okay, so our general fiber then is Fano, because we know that the restriction of minus Kx is minus Kf, which is also ample by Kleiman's criterion. So in this first case, it tells us the general fiber is Fano. So this is one of these Fano fibrations. But we also know a little more, again, by the same type of argument that R is array. We know that all the fibers have to actually be irreducible. Because if we ever had a fiber that broke up, then curves on one component of the fiber will be different numerical classes than curves on the other component. So we have general fibers Fano, and all fibers are irreducible. And so these types of extremal contractions, or maybe more generally Fano fibrations, where you obtained it from an extremal contraction, are sometimes called Mori fiber spaces. And then in that case, you could hope to understand X by understanding the geometry of Y and the geometry of Mori fiber spaces with base Y. So you kind of broke it down into smaller dimensional pieces. Okay, so that's this fiber space case of an extremal contraction. For a divisorial contraction, Well, there's not much to say right now, but maybe the important thing that we need, essentially by our proposition, the Picard number of x is the Picard number of y minus 1, because we've contracted a single irreducible divisor. So, plus 1. So y has Picard number 1 smaller, because we've just contracted a single irreducible divisor. And in this case, we need to know that the singularities of x, or of y, I guess, singularities of y are nice enough to continue. So ideally we want y to be q factorial. So that then it makes sense to ask, does y have an extremal contraction? And then it makes sense to apply the previous proposition to this extremal contraction of y and keep going to somehow simplify the birational geometry. And it's also important here that the Picard rank drops. So that's another measure of saying that after divisorial contraction, y has simpler geometry than x, because it has smaller Picard rank. So the cone of curves is in a smaller dimensional vector space. So it's going to be easier to work with. Okay, and then the third case in the small contractions, here we have some issues. One, the Picard rank doesn't drop. Because you're not contracting any divisors. But even worse, ky can't be q factorial, or q Cartier. So not only is y not q factorial after a small contraction, but actually even the canonical divisor, like the most important divisor of the minimal model program, is not q Cartier. So nothing even makes sense to try to talk about the Cohen theorem or anything on y. And the reason for this is because, like, on the one hand, we know that kx.c is strictly less than 0 for any c in the fibers. But on the other hand, if you have a small contraction, then you have to have that f upper star ky equals kx. If ky is q Cartier. So suppose ky is q Cartier, then its pullback has to be kx, because they're the same away from a high codimension set. So they have to be the same as divisors. But if you're pulling back, then kx.c is the same as the pullback of ky.c is the same as ky dot the push forward of c has to be 0, because c gets contracted. So that's a contradiction. So this tells you that ky can't be q Cartier. Okay, so we have to deal with that if we want to be able to apply extremal contractions to keep going to simplify the geometry of x. So for that, we have definition of a flip. So let's say that f is a small contraction, small extremal contraction of a kx negative ray. Then a flip of f is a birational morphism f plus from some other variety x plus to y that fits in a diagram like this. So here's our f, here's our f plus. In particular, x and x plus are birational because they're both birational to y, with the properties that, one, f plus is also small. So it has no exceptional divisors. The exceptional locus is higher codimension. 2, kx plus is q Cartier. So at the very least, we've resolved the singularities of y a little bit so that the canonical is q Cartier, so we have hope to keep going. And then 3, it's like the opposite of our f. Kx plus dot any exceptional curve is strictly positive. So we can kind of summarize the situation in that in this diagram, minus kx is ample, is f ample. We'll talk about relative ample a little later, but it's what you think it is, that it's strictly positive on curves. So for f, minus k is ample, and then for f plus, k is f ample. So you can think of it as kind of extracting these curves where that are on the negative side of the cone, and then gluing back in curves that are now on the positive side of the cone. Because now they intersect positively. So in that sense, we haven't dropped the Picard rank, but we have kind of killed off an extremal ray on the negative side, if these flips exist. Okay, so now the big question, do flips exist? Which we'll talk about later. Or maybe when do flips exist? So that was one of the big motivating problems for the field. And now we can describe a strategy for classifying varieties in higher dimensions. So first we have to identify some class of singularities. That are closed under, well, first I guess that such that the cone and contraction theorem holds. For varieties with these singularities, and such that they're closed under both divisorial contractions and flips. So we identify some class where we can understand the cone of curves using the cone theorem, where extremal contractions exist, and where we still land in this class after producing extremal contractions or flipping if we need to. And then 2, we need to know existence of flips. And then using 1 and 2, what do? We start with our x, and we ask, does x have an extremal ray? If not, then we can't say anything, or maybe we'll say something later. If it does, pick an extremal ray and produce the extremal contraction. If that extremal contraction is divisorial, then we just take the image as the next variety in our program. So let's write it this way. Yeah, take our extremal contraction. So pick a ray and contract it. Now we'll end up on some x1. If this was divisorial, then we repeat with x equals x1. But if it was small, replace x1 by a flip. We'll call it x1 plus, and now take x equals x1 plus for our next step. Or the third case, if it was a fiber space, then we just are done and we use induction. So this is one step in the minimal model program. And then we keep going until hopefully this process terminates in one of the following options. So let me just write it as a sequence of birational maps, where at each step kind of we take as input either the image of a divisorial contraction or the flip of a small contraction as our input. And then at the end, we terminate with either a fiber space or a minimal model, i.e. KXM is NEF. Those are kind of our two possibilities. Those are the two places where now we've stopped, where we can't apply the algorithm anymore. Either there are no negative curves, and then we have something where KXM is NEF, and we'll call it a minimal model, or we've contracted to smaller dimensions, and now we're in a new situation in smaller dimensions. So the big, so then at this point, once you've kind of defined your algorithm, now the big question is termination. And it's really the flips that are the problem, because if you just have divisorial contractions in this algorithm, then every time you're dropping the Picard rank by 1, and so it has to end because the Picard rank is greater than or equal to 0. So eventually you have to be done. But with flips, you don't change the Picard rank. So it's possible that you just have an infinite sequence of flips that never terminates in one of these two cases. So that's another kind of big open question. Do all sequences of flips terminate? And then finally, you want to understand this minimal model. So 5, and there we have the higher dimensional abundance conjecture. Okay. Okay, so now that we have a maybe more clear outline of what we want, let's go all the way back and prove some positivity statements that we skipped at the beginning. Yeah, so maybe like from here, we want to start working with varieties with divisors. We want to really cement our techniques and understanding for working with linear series, and then we want to prove some vanishing theorems that will go into proving that the cone and contraction theorem are true. So that's why we're going back to kind of actually prove Kleiman's criterion to get used to working with divisors. Are there any questions before I start that? Okay, so I didn't define intersection numbers with higher dimensional subvarieties, so let's do that right now. And the definition is the same as intersecting with curves, except that we have to kind of use a trick of going through amples. So let's say that H is an ample line bundle. Then some large enough multiple embeds X into projective space. And so now under this embedding, we can define the intersection of H to the dim W times W, where W is any subvariety. we can just define this as 1 over m times the degree of W embedded in this projective space via phi. And now, here's a very useful lemma. If D, let's say for now effective, but really for any divisor, but at least if D is effective and H is ample, then D plus MH is ample for any M large. So then now we can define the intersection of D to the dim W times W by linearity. So just and then let me restate the Nakai-Moshe's own theorem in general. Which we're about to prove, which tells us that we can pick out amples by intersecting with arbitrary codimension subvarieties. So let's say D is Cartier, then D is ample, if and only if D to the dim W dot W is strictly positive for all W. And here, let's assume X is projective to begin with. Okay, so we'll finally prove this, and we'll use it to prove Kleiman's criterion. So the first direction, if D is ample, then it's clear that it intersects any subvariety strictly positively because the degree of any subvariety of projective space is strictly positive. Or equivalently, any positive dimensional subvariety intersects a hyperplane. Okay, so the hard part is the other direction where we assume something about intersection numbers and get something about the actual linear series or the actual space of sections. So first, we can suppose that X is irreducible. If you have some divisor whose restriction to every component is ample, then the divisor is ample. So we're going to induct on the dimension. So we're going to suppose that we know for all varieties of dimension n minus 1, or up to dimension n minus 1, then this criterion holds. And now we want to show that some divisor is ample on X itself. So our induction tells us that D restricted to Z. Well, this intersection numbers are compatible with restrictions. So if we assume this property for all W and X, then it's going to be true for D restricted to Z. So we know that D restricted to Z is ample for all proper subvarieties. By our induction hypothesis. So step one then is to use that to show that the divisor D has a lot of sections. And in fact, so we need at least that it has sections for some large enough multiple. But actually, we're going to show that the argument really shows that D is big, that its growth rate of sections is actually maximal. Okay, so to do that, let's look at, let's pick some H ample, so that D plus H is ample. Let's even say very ample by making H even bigger by multiplying by some large multiple. And so let's take some hyperplane class for D plus H. Let's call that A. So now we're going to look at two exact sequences. So we have the restriction sequence for our H. And then we also have the restriction sequence for A. So the restriction sequence for A. Okay, so let's look at the long exact sequence, say for the first one, but we're going to apply the same argument to both. So we know that D restricted to H is ample. So we know that its cohomology vanishes if we twist K large enough. So for star, we know that H1 OHKD is equal to 0 for K large. And so we know that the higher cohomologies of KD minus H are the same as the higher cohomologies for KD for all I greater than or equal to 2. But we can apply the same. So this is just by looking at the long exact sequence because of this vanishing. Really, this is HI for I greater than or equal to 1 on on H, because D is ample on H. And so we get this equality for I greater than or equal to 2 on X by the long exact sequence. But then from double star, we have the same thing for that sequence. So we get that OX KD minus H is equal to HI OX. Now we have K plus 1D because A was a section of H plus D. So these are also the same for I greater than 2 and K large enough. So that implies that these two are the same. So this tells us that the cohomology of D actually stabilizes as you keep twisting higher and higher. But then we can write down the global sections. This is greater than or equal to H0 minus H1. Because H1 is the thing we don't know about from this argument up here. This is equal to the Euler characteristic plus a constant. That's what the argument proves, that H0 and H1 are the only things that are actually varying for large enough K. And now we need a weak generalization of Riemann-Roch to higher dimensions. So we just write it as very weak Riemann-Roch. The Euler characteristic of OX KD is equal to, or let me write it in terms of a variable t. So kind of for any twist as a function of this indeterminate t. This is d to the n over n factorial t to the n plus lower order terms, where n is the dimension of x. So by very weak Riemann-Roch, this term is equal to d to the n t to the n over n factorial plus lower order. But now our assumption says that this is strictly greater than 0. The leading coefficient there is strictly greater than 0. And the difference between this Riemann-Roch formula and h0 minus h1 is just a constant. So we can absorb that constant into these lower order terms and see that h0 is greater than or equal to something with positive leading term plus lower order terms. Here I should have put k since I had k twist. Okay, so that tells us not only does D have sections, but it's big because it has this kind of maximal growth rate. Okay. So step 2, we want to show that D is actually semi-ample. Some large enough multiple of D is base point free. So let's just, because we can replace D by any multiple, let's assume that we've replaced D by a large enough multiple so that D is effective by step 1. Then we want to show that OX of KD is globally generated, i.e. the linear series KD is base point free for some large K. Okay, so let's pick some effective divisor, so some section of D. And again, we're going to look at the restriction to this effective. So we get 0 to OX K minus 1D to OX KD to OS of KD. And now this term is globally generated by our induction hypothesis. All right, so this last sheaf is globally generated by our assumption, but we also know that away from our S, we have no base points because S is one of our sections. So we just need to show that there are no base points on S, which is to say that this map induces a surjection on global sections. Okay, so we need to show that that restriction is surjective for very large K. So the easiest thing would be to show that the H1 vanishes, but we don't know that for sure yet. So instead, we're going to show that the map on H1 stabilizes. So basically, like in step 1, we know that this H1 on S is 0. Again, by induction. So this tells us that the map on H1 on X at the beginning of the sequence is surjective for every large enough K. But that means we have the sequence of surjective maps on a sequence of finite dimensional vector spaces. Eventually, they have to stabilize to the same map. Maybe they're not 0, but whatever happens for large enough K, because at every step they keep being surjective, eventually they have to all just become isomorphisms. But if they're isomorphisms for large enough K, then that exactly tells us that the restriction map is surjective by exactness. So that tells us that KD is globally generated. So we have a morphism to projective space. And now step 3, by step 2, we know that we have some phi for large enough K that's actually a morphism onto projective space, and such that KD is the pullback of the hyperplane on projective space. But now the last claim is that phi has to be finite. And this again is by assumption because D dot C is strictly greater than 0 by our assumption. But this is the same as H dot phi of C. So that tells us that phi of C can't be contracted to a point. Phi of C has to also be a curve. So phi restricted to every curve is finite, but being finite is a topological property, so phi is also finite. Well, topological property for proper maps. Okay, and so now we can finish by this kind of basic proposition about ampleness, which is that if you have a phi from x to y that's finite, and L is ample on y, then phi upper star L is ample on x. And this is using the cohomological characterization of ampleness, that higher cohomologies vanish whenever you twist any sheaf by your ample. I guess I can just write it down quickly, and using that for finite maps, you can compute cohomology upstairs or downstairs. So this cohomology is the same as the cohomology of the push forward using ampleness. This should be a phi. But so this is finite. And then projection formula tells us that this is the same as phi lower star f tensor m copies of L. I'm sorry for abusing the notation. Twisted by m copies of L. And then this is 0 because L is ample. And so our original cohomology was 0. Okay, so that was a sketch of that. So once we know this proposition, then we know that KD is ample because the pullback of an ample on projective space by a finite map. Okay, so corollary 1 is that being ample is a numerical criterion, meaning that if you have two divisors that are numerically equivalent and D1 is ample, then that implies that D2 is ample. And then the most important corollary is Kleiman's theorem, Kleiman's criterion, which is why we prove this. But to do that, we need a intermediate, which is another theorem of Kleiman, which is that if X is projective and L is nef, then L to the dimension of Z dot Z is strictly greater than or equal to 0. Sorry, not strictly, it's just greater than or equal to 0. So this is like the weakening of the Klein-Moishezon to nef, but it's only one direction. So what we just proved is that you're ample if and only if this intersection is strictly positive, and now this is saying if you're nef, then this intersection is not negative. Where again, nef is defined by this property just on curves. So the definition of nef is that L dot a curve is greater than or equal to 0, and this theorem is telling us that the same holds for higher dimensional subvarieties. Okay, and we're going to need this to actually prove Kleiman's criterion about the effective cone. So again, we'll induct on dimension. Because we know for curves, because L dot a curve is non-negative by definition of Neff. And so our induction tells us that the thing we want is already true for every subvariety except for X itself. Again, assume X is irreducible. So we just need to prove that the top intersection number of L is greater than or equal to 0. And let's just call this N. Okay, so that's what we want to prove. So to do that, let's write down this auxiliary polynomial. Let me get my notation right. XL plus YA to the N, where L is the thing we want to, L is our Neff divisor, and then A is some chosen ample, or maybe very ample. And so if we expand this out, what is this going to look like? It's going to be X to the N, L to the N, plus some terms like this, and then plus a term corresponding to A. Okay, but now A is very ample. So A to the I, we can compute this L to the N minus I times A to the I by first intersecting this very ample hyperplane I times to get some subvariety, and then intersecting that with L, the complementary number of times. So this is greater than or equal to 0 by our assumptions, because these A to the I's are lower dimensional varieties. And this is strictly greater than 0 because A is ample. So by Nakai-Moshe's own, or actually by definition of ample. Anyway, so okay, so those coefficients are non-negative, and that coefficient is strictly positive. So that tells us that if we plug in 1 for x, then this is some polynomial where all the coefficients are non-negative and the leading coefficient is positive, except for the constant term. So the only thing we don't know about here is the constant term, but that's enough to show that this is an increasing function of t. On the other hand, suppose that L to the N is less than 0. But then L to the N is the same as the value of this polynomial at t equals 0. So that tells us that f10 is strictly less than 0. But we also know that it increases to become strictly positive eventually. So there exists some t0 greater than 0 with f1 t0 equals 0. And now let's approximate this by some rational number. So pick t1 rational. That's a little bigger than t0. And let's see what happens for this t1. Well, right, so then L plus t1a, this is some Q divisor, so multiply it to clear denominators to make it an actual Cartier divisor. So L plus t1a dot, I don't want to say it, yeah, dot NEZ now is strictly bigger than 0 because it's our L, which is, sorry, yeah, We know that by induction, L, like for any z that's lower dimensional than x, for any proper subvariety z, this L term intersects to be non-negative, and then all these ample terms will be strictly positive. So we know that this is true for any z, a proper subvariety by induction, because now we've added some non-negative multiple of an ample, so we've made things even bigger. But for just the top intersection number itself, this is equal to F1 T1, which is strictly bigger than 0 by our observation that F1T is increasing, and T1 is bigger than T0. So that tells us that L plus T1A is ample by an Klein-Mosher zone. Because for every subvariety, you get something strictly positive now that we've kind of perturbed it by some ample. Okay, so then let's compute L plus T0 A. So this is the same as L dot so we just split up into its two terms. So now this piece is the limit as Ti, or as this T1 approaches T0 from above, of the intersection with this T1A, which is ample. So this whole thing is greater than or equal to 0 because it's the limit of something with intersection strictly greater than 0. On the other hand, here we have ample times L plus T0A. So again, this L plus T0, what do I say here? I wanted to argue that this is strictly positive because A is ample. Oh, right, yeah. If we expand this out, like A dot L is greater than or equal to 0 by our assumption. Again, because A is lower dimensional. So we have our inductive hypothesis there. So any terms that involve A and L are greater than or equal to 0, but the last term that involves just A is strictly greater than 0 because A is ample. So that's why this whole term is strictly greater than 0. And that's a contradiction. Because this T0 is positive. Because that was our bad assumption, was that at T equals 0, we had something strictly negative. So we're 0 at this positive T0. Ooh, okay, so that tells us that this top intersection number is actually greater than or equal to 0, and that completes the proof. Okay, and now in the last 7 or so minutes, we can finally prove Kleinman's criterion. So in the notation introduced last time, this was that D is ample if and only if the half space D greater than 0 contains the cone of curves minus 0. Okay, so for one direction, suppose D is ample. Then let's pick a basis for n1 of the form d equals d1, and then some other divisors up to the Picard rank such that di are all ample, not just d1, and also such that 2d minus di are all also ample. So we can do this by applying that previous lemma that if we add a large enough multiple of any ample, we get an ample. So any effective, we can kind of add some ample multiples to make it ample and still get linearly independent divisors. And then by scaling d to make d even larger, we can get that this 2d minus di is ample for every I by just scaling d by some very large multiple. Okay, so we have this basis with these ample properties. So now let's define a norm on our space of curves as just the sum of the intersection numbers with our basis elements. But then to make it a norm, take the absolute value. On our numerical on our space of numerical curves. Okay, and now we're going to compute 2 row of x d dot x. Let me use z because now I want z to be a pseudo-effective curve. One of these things in the closure. So take some non-zero z in the closure, and now we want to compute something about d dot z, and we're going to compute it by using this norm. So let's look at 2 row of x d dot z minus this norm of z. If we expand this out, so because we're in the pseudo-effective cone, then we know that each of these intersections are non-negative because we know just by definition of ampleness that they're strictly positive on the interior, and on the boundary they can't be negative. They have to be at least 0. So we can drop this absolute value in this definition of the norm. So we get 2 row of x d dot z minus some di dot z from I equals 1 to row of x. And now factor these things out. We get row of x d minus 2d. I don't want to write this. Row of x times the sum of 2d minus di dot z. So factored out using linearity. But now our assumption is that these 2d minus di are also ample. So this whole thing is greater than or equal to 0. Because each of those summands is greater than or equal to 0. So this tells us that 2 row of x d dot z is greater than or equal to 0. Is greater than or equal to the norm, which is strictly greater than 0 because it's a norm. So d dot z is strictly greater than 0. Okay, so that was one direction of Kleiman's criterion. And now we have the other direction. So suppose d dot z is strictly greater than 0. For all these pseudo-effective curves. Then pick a that's ample such that td minus a, and then pick t as well. So fix an ample and pick a t such that td minus a is nef. So yeah. Okay, so then call this L. Then we know that td is equal to nef plus ample. But then by our previous theorem, if we compute TD to the dimension Z dot Z, this is going to be L plus A to the dimension Z dot Z. And now the terms with L are going to be strictly are going to be greater than or equal to 0, but then the term with A is going to be strictly greater than 0. So this whole thing will be strictly greater than 0 by the previous theorem. So D is ample by Nikai-Moshe's zone.